Good afternoon and welcome back. I know the session after lunch is tough to keep you awake, but I guess the last session of the day is even worse. We just have one good thing, we have air conditioning here, so I never found it so easy to get people back in the room. It's amazing. It's a great trick. Okay. So what we'll do today is entity authentication and symmetric key establishment. So you heard this morning about symmetric key, where you shift protection of data to keys, and public key, where you use public keys to authenticate data or establish secret keys. So, but now we will see how you integrate this. So we'll explain to you entity authentication. We still talk about passwords. I think somewhere in the 90s, Bill Gates announced the end of the password, but I keep having more and more passwords stored everywhere. So I guess we will see finally less and less passwords, but at least not for now. It is still very important. We'll look at some subtle problems when you apply these things in practice. And then we look at high level at key establishment protocols and again, subtle attacks on those. So this is a slide I quickly went over this morning. But so more or less what we try to achieve, what we focus on is entity authentication. So this is you have the entities and you want to authenticate them. And unfortunately, cryptographers call this identification because Adi Shamir, who's a famous cryptographer, the S in RSA, he wrote a paper in 1985 called How to Prove Yourself, Solution to the Identification Problem. And so since then, cryptographers call proving who you are identification. Now, this is a big problem because the people from computer security or cybersecurity, so you get some people from Distunet tomorrow, like Frank Pieces and Tom van Kutsum and Lieven de Smet. They say if you go in front of a computer, entering your username is identification and giving your password is authentication. So they actually call identification something else. Who is right? I don't know. It's just confusing. And we'll talk about biometry. In biometry, in fact, if you go to a border crossing and you give your password or passport, what the border guard does is verification. Verifying that you're the person claimed in the passport. So in fact, for similar things, we use different names. I don't have the answer, but be aware of this. The only thing I would like to say is don't use authentication without saying what you authenticate. Either the entity or the key or the device or the library or whatever you're authenticating. At least I think it's bad practice to use the term authentication because you really should indicate what you authenticate. Okay, so the problem is easy. We look at passwords, although it's old-fashioned. We look at challenge response with symmetric and public key, and then look at biometry. The problem is very easy. You have a connection between two users, and one user says, "Hi, I'm Alice." And of course, the question of Bob is, why should I believe her? Why should you believe that this is the person claimed to be? If this problem happens, we gave a scenario of a border, or you go to an ATM machine, if you can still find one in Leuven, you want to withdraw money. How does this device know it's you and has to take the 50 euros from your account? Of course, a more common case is you're on the internet and you want to prove your identity. Or the government insists that you prove that you're older than 18 to visit certain sites. This is the more plausible scenario which will be imposed on us in the coming years. So identification is defined. This is a definition from the Handbook of Applied Cryptography, an old book, but it's still very useful. It's available free online as that you're corroborated of the identity of another party and the fact that this party is alive. So this is the difference between data authentication, where somebody authenticates a document or a piece of software or a file, and they say this is coming from me or from this computer, and you receive this document. There may be a timestamp in there, but in any case, if a software update is authentic today, it's also authentic tomorrow and also a week later and a year later. So this is something that is over time. Well, empty authentication has a notion of a session, of somebody appearing in front of you, and is this person there? There's a notion of liveliness. The way I explain this to my students is a terrible example from the press from like 20 years ago. In South Africa, there are some people who can't write. And so when they collect their pension money, they go to the post office and they put their fingerprint on a document. And this is how they authenticate that they are there and that they got their pension. So there was a horror story in the newspaper of somebody who passed away, but the children still wanted to collect the pension. Can you imagine what they did? They took the body in between them to the post. I mean, okay, you can read the story in the newspaper. So, but it makes my point that authentication wants to check liveliness, right? That you have to be there. There is a notion of a session and something that has to happen in real time. It's not something over time. What you learn in all the textbooks is it's about something you know, something you have, and something you are. And you can all remember that. So what you know can be a password or a PIN code. What you have is a microstripe card or a smart card, or increasingly some string of bits on your smartphone is also considered as something you have. And then something you are is biometrics. And of course, it's also increasingly being used. It was initially only for military or nuclear sites, but today, of course, all our smartphones have this technology. It's very low entrance and very cheap. But in fact, there is also behavior biometrics. That's not a static property of you, but how you behave, like how you hold your phone, how you type, what kind of things you're doing. This is, again, this get security by violating privacy, collect all kind of information. So, for example, a lot of the banking software looks at your phone and all the devices, all the applications on your phone, the contacts on your phone, and so on, to find out that this app is really sitting in the same phone as it was the day before or an hour before. So it's kind of checking the behavior and the context to find out the identity or the specific user. And then getting more and more important is also location. And this was in the old days, when people used dial-up modems. I guess this is before time of many of you. In fact, the company would call you back because also the phone line was expensive. Again, something that people can't understand, that you could actually pay something like 25 euro cents for 5 minutes call. But so there was this dial back thing. Was also an authentication mechanism to use the phone system to find who you are. But of course, increasingly we get GSM, Galileo, Baidu, GLONASS, I guess Starlink. All these systems will actually determine where we are. Also, your phone knows more or less where you are. There is many techniques. For example, there is, of course, GPS, which you can switch off. But it's well known that Android devices, and I assume also Apple, look around which Wi-Fi networks they see, and then based on that, they know where you are. Because some people leave Wi-Fi and GPS on, and from this you know where the networks are. And then those people who put Wi-Fi on, they actually know where you are from the Wi-Fi networks you can see. And if you switch off Wi-Fi, then the Android phones once in a while switch on the Wi-Fi to see where they are. So location is something which is also increasingly important, which is not in the obvious tree of know, have, and is. So now it's actually also how you behave and also where you are. And of course, these last two are also particularly intrusive. So still back to passwords. So they were invented in the 70s because there were more than one user than on a system. But of course, it's a terrible system because people use bad passwords, like the name of their dog. And then a big problem is that you can listen to the channel intercepted. And this was okay if the channel was from your terminal to the mainframe 10 meters further, but as soon as the LAN came, it was a disaster. I still remember in the 80s when we saw LANs in the building, you just put a sniffing device, you put your network card in a listening mode, and then you could, on the Ethernet, eavesdrop all the passwords. And then it got even worse with the internet, of course. And then, of course, Bob has your password as well, which is also a problem because users tend to share passwords between applications, so we use passwords. And then finally, you have to have secure storage because if the database with passwords is leaked, and unfortunately this happens, remember the bubbles from this morning? There is very often passwords there. Then you have also a problem. You can go to the website Have I Been Pwned and find out whether your passwords are there or not. But so it's a terrible system, but we use it because it's cost effective and the service provider can shift the cost to the user. And this is why we keep using them in spite of all the predictions of Bill Gates. It's an economic issue. And also, if you're a startup and you have a great idea, if you're going to ask your users to first order a physical hardware token before they become your customers, you will be out of business before you have your first 1,000 users. So you just do it because this is what users know how to do. But so because of the interception, it can also be replayed. And in fact, the password does not give liveliness. So if you stick to my definition of before, in fact, a password does not provide any authentication. But we'll still discuss it. There's some small improvements also found in the 70s. You can hash the password with a hash function. And then at least if somebody compromises the server, they don't find the passwords, only the hash passwords. And then they have to search through the passwords to find the hashes. That's a small improvement at a low cost. There is some problem, namely that computers were slow in the 70s. Today they're very fast, but the capacity of our brains has not grown. Okay, that's the problem. So what we can remember, say, is lowercase and digits. Maybe we can remember 8 characters, lowercase and digits. Well, that's something like a 40-bit key. That's not very good, because that you crack in a few milliseconds or seconds. And so this was maybe good enough in the 70s, but it's not good enough today. And if you want something which is like 10 characters to full keyboard, which will not really work, but okay, if you imagine you can't remember this, then in fact you get a 64-bit key, which is again not enough. This is like a desk key, it's insufficient. So our memories are not capable of memorizing 128-bit passwords. It's a bit better with passphrases, but who wants to type 20 characters every time they have to log in? Anybody here? No, okay. So you just use short things, and then at the end of the month you add a 1 and then a 2, and I mean, you all know, okay. Good. So there is a bit improvement, more improvements called salting. It's a very simple idea that you give every user a different function by having a public parameter called salt, which you publish also in the database. Well, you make in the database, there is no need to publish a database, but Unix used to do this under etc.password, but maybe not the best idea, but that's what they did. And so you have a public salt and a public that's used in the function. And so the advantage is that if 2 users share the same password, that you can't see it from the database. Or if you want to run to a dictionary of 2 million passwords, you have to do it for every user, because the idea is that every user has a different salt. So in fact, you can gain quite some security by using random salts. We found out, for example, that Matter, so Matter is an IoT system that's being pushed by all the big techs, actually uses the same password for every device. So if you have a certain dishwasher or router or whatever thing with a certain serial number, I mean the model number, then you had all the same salt. So more or less defeating the salt effort, because every device should get its unique salt. Some people were not paying attention in my class when I was explaining it to them. Or I guess they didn't take a crypto class, they didn't understand the notion of a salt. Okay, so it kind of helps a bit, but it's still not great. So then people came up with better ideas, because in cryptography, as you heard this morning from Tim, so the idea is to make things as fast as possible. But then people said, what if you make it as slow as possible? Because in fact, this password verification only has to be done after this dumb user types with 2 fingers their password. So anyway, that takes them half a second. So you can also spend half a second to actually check the password. So this function can be slow. And so this was actually already in the first password system, but with 16. But today you would say use like 1 million or 100,000 iterations. So instead of applying the function once, you apply it 1 million times before you check. And so that takes typically then something like 100 milliseconds or a second. And so this means more work for the server side. But on the other hand, if the password database gets leaked, it takes you every time a second to test one password. So rather than increasing the capacity of the human brain, you make it harder to check for a password. This is actually a better solution, because you shift the work to the server, and the server has computational power. And then, of course, you can start building special hardware for this. So people actually came up with functions which you cannot speed up with special hardware. And what is hard to speed up? If you have a large memory and you do random accesses in this, then you have a bottleneck. In fact, if you have this kind of problem where you have a gigabyte of memory and you do random access on your PC, it will be reasonably fast, or in the server with a gigabyte it will be reasonably fast to do the hashing. But if you build special hardware, you actually have to spend a fortune on RAM memory, and the RAM memory will be the bottleneck, because a RAM memory access time is something like about 50 nanoseconds. So it's really slow. If you have to do thousands of lookups, you will take seconds to do the evaluation. And buying more hardware will not help in some sense, because the bottleneck will be the RAM access. So people first used things like MD4 and MD5, then they used PBKDF2, scrypt and bcrypt. They're already slower, but in Argon2 and Balloon, their designs are actually more recent designs that are deliberately slow. And so with those, in fact, you can have a relatively small password and still have a decent security level. Okay, so there is some problems. You cannot use such a system and then take the password file and use it on your Raspberry Pi. But the same password, because then it will take like 2 hours to log into your Raspberry Pi. So that's maybe not a fantastic idea. So that, or if it requires a gigabyte RAM, you'll never be able to log in because you just can't compute the function. So there is some disadvantage there. And then, of course, if you like Google or Facebook, you don't think it's a great idea. Because in Google or Facebook, at every moment there is 10,000 people logging in. And if each login takes you 1 second calculation, you need 10,000 servers to make them happy, which is actually very expensive. And so for them, they don't like to pay the costs. And this is why in practice, again, the iterations are lower. Same thing in Matter. The recommendations for Matter, they are actually using not so slow function, PBKDF2. And the recommendation is that you use 600,000 iterations and they use 1,000 or 10,000. So again, this is laziness. There was a very interesting talk at Real World Crypto by Meta. They were still called Facebook at the time. And they explained how they do password hashing. And Meta doesn't use a salt, they actually use a secret key. And we call this sometimes a pepper. So what you do is you actually hash a password with HMAC. Tim explained to you HMAC this morning. So this is a MAC algorithm based on a hash function. And so this means that only the server with the key can actually check passwords, which is a bit annoying. Also, if this key is breached, then you have not gained much, but at least I assume that Facebook has copies of these keys and backups, and it's reasonably well protected. But then if you look at their real system, what you do is you actually take MD5 with the salt, the password, then you hash this, and then the result you hash with HMAC, and then you hash the result with bcrypt, and then you hash the result with SHA-2. I always show this to my students because this is how cryptography looks in practice. It's just spaghetti. It's a mess. So why is this? Because the revenue of Facebook and Meta depends on the number of active users. Many users will not know their password anymore. So if you tell them we're changing our password hashing function, you have to log in again, then they will not be able to log in and they will not bother. So then the investors will see, in fact, they're not users of you. So what you do is you keep your old insecure MD5 and you hash it with HMAC, so you don't need the user for this. So you can upgrade your password system without bothering the user, without even having the user being present or ever knowing about it. And then I guess they realized that if this key would be MD5 is really crappy, then if this key would be compromised, it's not insecure, then they applied bcrypt, but bcrypt is a large result, so then they applied SHA-2. Welcome to the real world. This is how a password system looks. If you would design this from scratch, you would use Argon2 with a very nice parameter set, but this is not how the world works. Okay, and then some people dream that with LLMs we're going to re-implement everything, but I think these kind of things, if you touch the users, it will never be re-implemented. I mean, there's like billions of users, right? You don't want to, if you, as an engineer, as a security person, annoy billions of users, you will be fired. I can promise you. Okay. So there is other tricks. If you can't remember something, well, just store it. In the past, people used to store this on Mac stripes, right? You have your bank card, and they're now disappearing, but on the back you have this Mac stripe, and you can write actually 135 bytes on this. This is almost 1,000 bits you can write on this. It's a lot of material. It's not very secret, but everybody can buy a reader on eBay and read it. But at least you can put a key there or a hash of a key. And then about 25 years ago, USB keys became popular. And at that moment, you could store like, a few kilobytes on them. But today, of course, you can store 1 terabyte on these things. So there is enough key material to be put on there. But of course, this solves the problem. Now you can remember long keys. Well, you don't remember them, you put them on the device. And if you lose the device, you have a problem. Right, so this is nicer for the user. But now if somebody steals your device or you lose your USB key, you have a big problem. And again, there is no liveliness. The banking sector also invented something else called static data authentication by EMV. So what it used, just produce a statement saying user X is part of the system. okay? It's a bit like a membership card of your gym club. Okay, just has, in this case, your photo and a signature, I assume, of the boss that says this user has paid her fees or his fees. But instead of having actually your photo, you have actually your, what the financial sector calls your PAN number, personal account number, or your registration number. And it says this is part of the system. So what you have is, well, this is, of course, X509 stuff, so all telco stuff. So it has a distinguished name, which consists of a common name, an organization, and a country. This was still from the times in the 80s when the telcos were ruling the world, from CCITT in Geneva, and they thought there would be one operator per country, and they would make the rules for everybody. And then you have a serial number, a start and an end date, a place for revocation. We'll discuss that tomorrow. And then there is an entity, say the bank or a central party, that's just digitally signs this document. It's a bit like a gym card. Right? It says, now you're part of the system. And you can show this system, and the person can verify that this identity or this email address or this PAN number in the financial sector is a valid number, part of the system. And the nice thing is, verifying this only requires the public key. So now the verifier doesn't need any secrets, they just need the public key and they have to check, okay, this is an authentic signature, this person can be part of the system. In fact, this is used in the financial sector. It was used in EMV. It's also used in your passport. If you have a passport, which most of us have, with a chip in the back cover, there is actually a signature of your data signed by your government. And so any border agent can read this out using some information in the middle of your passport, the machine readable zone, and they can check this signature. So this is very annoying for the CIA because the CIA can no longer forge Belgian passports. Right? They can, of course, make fake passports, but they don't have the private key, and they can't say that John Smith is a Belgian citizen because they don't have the private key. Of course, what the CIA can do is they can find a John Smith somewhere and take their passport, read it out, and put it in their passports. So you can copy this, so it doesn't solve everything. So the nice thing is verification with the public key. Disadvantage is that these signatures are big, so you don't want to write them down by hand. You want to send them over a machine interface. And then, of course, they can be copied and intercepted. So I still remember, together with my late friend Fred Piper, the UK was going to introduce this for credit cards in EMV. And so we wrote a report saying, don't. If you put this on credit cards, and this is the way to indicate credit cards, what you will see is people will take their credit card or steal a credit card and take this field and put it in their own credit card and get free payments like this. And then the British bank said, this is very interesting, thank you for your reports, Professor, but do you know that a card that does this only costs 10 cents of a pound, while a card that can do RSA signatures costs £1. So this is 90 cents of pounds, and there is so many million Britons, so we're not going to do this. So they rolled out this system, and I can tell you, you can guess what happened, right? After a few years, they had to withdraw the system and replace it by signatures because people figured out how to create fake money. Again, so you have no liveliness, but it still has some uses in some settings. So if you really want secure authentication or authentication or device authentication where you test liveliness, you have to have challenge response. This idea was invented in World War II when you had the war over Europe, so where there was bombing raids. And so to make sure you wouldn't shoot at your own planes, you would send a challenge to the plane, and the plane had a module that would send a response back. And if the response was correct, you wouldn't shoot. If it was incorrect, you would shoot. And this was later introduced in other applications. So challenge response, which means a random number is being sent to you. And you have a key either in your bank card or in these kind of devices, although some of these devices don't have keys. You have to insert your bank card in there, but it's the same principle. And then the server has also a copy of your key. And what you do is you compute a MAC on this string. And this MAC can be quite short. I mean, recommendation of cryptography is 40 bits at least, or 64 bits, something like this. The Belgian banking schemes, they use 8 digits. And in some banks, the first 2 digits are predictable. So they think that 6 digits are enough. And also many systems online now. So this is now being replaced by an app on the smartphone with a secret key in there. And more or less, this is what's called second factor authentication. In the worst systems, this kind of MAC is sent to you over by SMS, which is really a bad idea. Even NIST thinks you should no longer do this because SMSs are really not very secure. So, but if your MAC is long enough, it's okay. If your MAC is too short, in fact, you have a problem because then you can start guessing. And if you can do it automatically, if it's 6 digits, it just requires 1 million attempts. You will say, oh, but then we block the attempts after 10 failures. Yes, but you have 1 million users, and I can try for every user at least 10 times. So I have enough attempts to succeed. So this is actually 6 digits is problematic. So you have to have other measures to deal with this. So this provides liveliness. It solves most of the problems. The main problem is that Bob still needs a secret key. By the way, IETF has standardized this called hashed one-time password, HMAC-based one-time password. So this exists and this is standardized, and you find this now everywhere. For the user, it's a bit annoying, at least if you have such an external device, because you have to type this random number and then you have to type this MAC. So it's almost tiring. You have to type 8 digits and then another 8 digits. For most users today, this is no longer acceptable. I really like it because at least I'm in control, but some people prefer to have something on their smartphone that goes automatically. But it does liveliness. So of course there is an easier system where the challenge is the clock. And so if you have a device with a clock, and then we'll send every minute, it will display a new MAC on the time. And then in fact you don't have to type the random number because the random number is the clock time. So this is kind of, it's not unpredictable, but it doesn't repeat. And so this is what people used to have in the 90s. They used to have a small device that would show a key every minute, and this is how they would log in. And today we have an app that does this. Of course, we don't buy devices anymore. We kind of trust this key in our smartphone because we all know smartphones are secure and nobody can read anything in the memory of a smartphone. So this is what we do, and it's easier than giving people devices. Okay, so it works. Also standardized by IETF, it works. There is some problem if the two clocks go out of sync, then you have to kind of find a trick to resynchronize them. So there is some nice patents where I guess they're now expired, but you get an extra challenge, and then this challenge is used at the same time to synchronize the clocks. So it kind of has a dual use, and you enter the challenge, you synchronize the clock, and then it's solved. There is just one problem here at Bob's side. There is a database, and if you have 1 million customers, then there is 1 million keys there. The banks know how to solve this. They only store one master key, and then they have the PAN number, and they encrypt the PAN number with this master key, and that is your secret key. So they only store one key, but not everybody did it like this. And so in, I think about 12 or 15 years ago, I went to look it up. There was actually one company called RSA that had such tokens, and they were market leader. It was actually very funny because they had this stupid technology this is actually technology from the 80s, right? I mean, a Mac, this is not high tech at all, but they made much more money than the company RSA. So they bought the company RSA, they called the new company RSA. Because the previous company was called Secure ID. They had their own Mac algorithm, which we also broke one day. So they were really, but it didn't matter, they made more money than RSA. But so what happened someday is that some employee of RSA got an email with a link to the vacation planning. And he clicked on it because he was desperate for a vacation. And you guess what happened? So some actor got access to the database with all the secret keys. And so RSA had, well, first we broke their algorithm. They had to issue everybody a new token with a new algorithm. And then a few years later, they had to issue everybody a new algorithm, a new token because their keys were leaked. And this was used by the military, by Lockheed Martin, by all the big tech providers, military tech providers in the US. So not a great story. So you really want to move to public key, because in public key, you do the same thing. You replace the MAC by a signature, and now you don't have a database anymore of public keys. You just have to have a list of authentic public keys. And more or less, if everybody says we're going to get rid of passwords today, this is what they promise to you. Well, either they promise you something like this MAC thing, but then in an app, which is really not the best thing because you still have the server problem. But this is really what you want people to do. And in fact, this system was already in the field in the early 90s by Canal Plus and other pay TV companies. And for the young people under you, Canal Plus and pay TV, that was the Netflix of the 90s. There were satellites up there. Even at that time, there were satellites up there, and they were showing you boxing games and football games and movies, and you could buy a dish and a set-top box, and then you would authenticate with a card to your set-top box, and then you would get the keys to decrypt the content. And they actually used public key style systems. Well, they used zero knowledge, but so this is the first large deployment of this stuff. And then the second large deployment is your credit card. So the EMV specs designed in Waterloo, 93, 94 by Europay. Actually there was the first global system, about 15 billion cards now, and probably more than 100 million readers, maybe more. So it's the largest public key infrastructure next to the web that exists and that uses this. It's fantastic. It solves all the problems because, well, it's really dynamic. Eavesdropping doesn't help. And you no longer have secret storage in the server. I guess the only question is, how do you get the public key of 14 billion users in all the Coke machines? That's an interesting question, but I'll explain that to you tomorrow. But this is, of course, they're not there. There is a trick with a hierarchy, but more or less this is what you have to do. The other problem is that signatures, well, random numbers, I guess they can be short if you're willing to take some risks. It can be like 8 or 16 digits. You could still type them. But an RSA signature, if you've been paying attention in Cran's lecture, today's like 4,000 bits. You don't want to type that. I assure you, you don't want to type 4,000 bits. Okay, and with post-quantum, it's going to get even worse. The signatures of post-quantum are not bits, but kilobytes, 1 or 2 kilobytes. You don't want to type this. So this means you have to connect this thing up to your PC somehow, and it has to be sent there. And this is why at home we still pay with our credit card with a super secret, non-guessable 3-digit code of every credit card. Okay, so we have a credit card that does public key, but we actually still pay with this super secret 3-digit code. And why is this? Because Visa doesn't want to be bothered with all these people who say, my smart card reader, plug it in the PC and it doesn't work. That's what nobody wants to deal with that. And these readers used to be expensive, now they cost nothing. But even then, nobody wants to deal with users plugging things in the wrong places and drivers not being up to date and so on. So this is why we have an insecure system. The other reason why we have an insecure system is that credit card losses for online payments are 2%. Okay, 2%. I mean, I don't know the exact number, but it's not very far off. This is the order of magnitude. Maybe you can ask Mike Ward tomorrow whether he can give you more recent statistics, but that's my guess. It's about 2% still. And who pays for this? The merchants. If you're a merchant and you have a fraud case, you get a fine because you had a fraud case and you have to pay the money back. And what does the merchant do? They increase their prices. So who's paying for all this fun? You. You're paying, and Visa is not going to solve the problem because it's not their problem. Right? It's only when the regulator will tell them, now you have to really make it secure, they will do something, you have to really use those cryptographic schemes. But for now, they still get away by not doing this. So as I mentioned, in fact, Canal Plus uses a more sophisticated protocol because in the early 90s, RSA was too expensive for smart cards, and Fiat and Shamir, in 1985, in their famous paper I mentioned before, they invented a system based on modular squaring. And so squaring is cheaper than RSA because it's only one multiplication, right? A times A. And so this actually what was rolled out in Fiat Shamir was a system where you have first a commitment, then a challenge, and then a response. And in that case, it's not that Canal Plus liked the complexity of having 3 steps, but that made the computational costs go down, and this is actually where zero knowledge was used. Of course, today zero knowledge is used also in cryptocurrencies like Zcash, and it's actually a core building block of cryptography, but I will not steal the thunder of Emad, who will talk about zero knowledge in a whole 1-hour talk later this week. But it's very cool because you can actually prove that Bob really only learns that he talked to Alice, and he can't use any information. So it's very nice. There is only one big problem of zero knowledge, is that Bob can't prove to anybody he talked to Alice. And this is good for privacy, but you can see the banks don't like this. Because there is a protocol, and the bank is now sure she talked to Alice, but if she writes down everything she saw, there is no evidence she actually ever saw Alice. And why is that? Because in zero knowledge, anybody can make a transcript that's valid without knowing the key, the secret key. So it's only when you were there, you know for sure it's valid. It's comes from a real key. But if you do it afterwards, then anybody can produce it. So it's no evidence value of an interaction. So this is why banks hate this, because they want to be able to have proof that you were there and that you authenticated. And so this is why we will not see zero knowledge in the banking sector, because the banks hate it. Okay, this is kind of an attempt to summarize all this stuff. So you have, like, can you guess the secret? This is a problem for passwords. Can you eavesdrop the channel? This is a problem for everything that's static. Can Bob impersonate? It's for everything with symmetric key. You have a secret key at Bob's side. Does Bob need secret key? Well, for static verification, he doesn't. For a static identity, but of course he can still forward your content. And then do you have a proof? Well, that's only in zero knowledge. You really have a math proof that somebody was there and that you can prove you don't leak more than the fact that you were there. But then you don't leave evidence that you were there, which is a problem for some applications. Okay, so now on to Google security keys. So the famous YubiKeys, all the other systems. So it's actually amazing that the Europeans managed to convince the rest of the world to use smart cards, because the Americans hated smart cards, not invented here, they don't want it. So for the whole world, for credit card payments. But on the internet, we were still using, strange enough, passwords. And so finally, Google pushed a solution in the FIDO Alliance. So one of the things, of course, is if you want to do something on the internet, then all the players have to agree, at least Google, Microsoft, Apple, a handful have to agree, otherwise it doesn't fly. And so this is the FIDO Alliance, where FIDO stands for Fast Identity Online. And so in 2016, Google actually gave a talk at Financial Crypto, and they explained how they rolled out 60,000 of those keys. At that time, there were about 60,000 Google employees, more or less to authenticate Google users. And amazingly, the users were happy. So of course, if you still go to events, people from banking or military, they have these smart cards, but you never see them smile because it's always a misery. The card doesn't work, or they forgot their card, or they still have to enter a password or whatever. So it's not really great. Also, at some moment, Microsoft was convinced by the Europeans to put smart card readers in all PCs and have interfaces for it, but then they removed them again because it was too much misery, right? This kind of the interfaces and the drivers and the middleware, and you don't want this stuff. But so now it actually works. There is one subtle difference, that this security key has a button to press. Maybe I should first explain you how it works. It's actually a terrible slide. I should make a better one, but okay, you can look at it later and figure it out. Maybe I shouldn't even show the slide. I should just tell you how it works, and you can look at the slide later. So the thing is, if you want to authenticate to a new website, you make a key pair, public-private key pair for this website. Okay? But the problem is, we all visit hundreds of websites, so you can't store hundreds of those key pairs in your token. And also, if then your token is compromised, you lose all your private keys. This is really annoying, right? So it's kind of inconvenient, and it's a problem. So the idea of Google is very simple. So you go to a website. Of course, you have to somehow establish first, use the TLS connection identity of the web server. We'll talk about that tomorrow. And then you make your key pair that you will use to authenticate at the web server. So you somehow create a new user account, or you link yourself to an existing account in some way, somehow having a QR code or some authorization to link yourself. And what you then do is you encrypt your public and private key with a key on your USB token. Okay, you just symmetrically encrypt your keys, and you send them over to the website and say, next time I come, give me back my keys. So in fact, the web server stores your key pair. So next time you show up, you actually say, hey, it's me again, give me my keys. And the web server sends you your keys. Of course, it keeps a copy of the public key, but it sends you the encrypted keys. You decrypt them with your USB key. Now you have the private key. The website sends you a challenge. You sign it, and then your authentication is done. So it's more or less the same thing as I showed you before. So as this protocol, very simple and elegant, but rather than having the secret key stored in a device, you store the secret key encrypted on the website under a symmetric key that you have in your YubiKey. That's like the egg of Columbus. Like, why didn't I think of this? It's so simple and so elegant. So you can log in everywhere, and you can have as many logins as you want. And of course, there is still typically a PIN code or a password to activate the USB token. There is also something else, which I think is a great invention. There is a button here. So why is this button there? Yes, sorry? To prove liveness, indeed, because if you work for Google or some other company, you have this in your device the whole time, and you want to prevent that malware uses this token. So in fact, to use the token, you have to push a button. Very simple interface. The only problem is that they moved from USB-A to USB-C, and now they have nano devices, so if you have big fingers, it becomes hard to use, but for the rest, it becomes smaller. But that's more or less how it works. So it's a cool idea. So this is the details. This is 502, so it's called C-type client to authenticator protocol. I will not give you the details. This is just more that you can find more details if you want. And then the web authn W3C protocol using RSA. And so more or less, this is how things now work. So if you have things like passkeys, have you heard of passkeys? So this is more or less what you do is you have somewhere a secret on your device, or you have a PIN or a password. Your keys are stored with the server, and then you ask for the encrypted keys, then on your device you decrypt them, and this is how you then log in, using the simple protocol. This is fantastic, unless of course you have a PIN 1234 and you lose your device. Because then you're completely cooked, right? Then people can use all the passkeys activated for your device to log in everywhere. So it's kind of a lot of convenience, but in the end, it's not so different from having all your secrets on a smart card or a USB token. It's a bit better. You never leak them, but in the end, if you lose your device and you don't have extra additional protection locally, well, then you're cooked. But at least on the internet, it's now using public key, which is amazing. Yes?
Like regarding the scenario of being losing, for example, you lost your key. So it is being exposed to like maybe exploit, or is that can be discontinued by the IT manager or something like that?
Yeah, there is of course revocation mechanisms. If you know you're exploited, there is revocation mechanisms. But if a nation state hacks your device, you probably don't even know, right? But yes, of course, if you can revoke these things, and this is where all the problem is. Huh? I mean, I can also tell you that in several companies where they use these YubiKeys or these Google authenticators or whatever 502 authenticators, people have multiple because they lose them, or if one breaks down and then they can't work that day. So the first thing that happens, you say, okay, now I'm going to order three more, right? Which, of course, you want to do your job. So there is also other problems there as well. But the reason why I want to explain this is that actually it's not so new, right? This is all actually early 90s stuff that only got implemented and got popular, and now it's called passkeys and FIDO and whatever. But in fact, it's all stuff that was more or less, for the first time, trialed at large scale by the pay TV companies and by Europay in the early 90s. But then, of course, it has to have the right form factor, the right cost. By the way, these UB tokens are very expensive. And some French researchers managed to get the keys out with a side channel attack recently. So in KU Leuven, we have a mobile authenticator that actually has some security advantages. It was a startup. It has been acquired since then by ItsMe. But so it's still used by millions of users, including 70,000 volunteers of the KU Leuven. It has some additional authentication features. So it's a very neat system. Personally, I think it's nice to use. It became slightly less nice to use because, of course, as everybody switches to these kind of authenticators, there is now new attacks where you get bombarded with random requests, right? And so if you make no friction to approve a request, then you actually risk to log in inadvertently. And so more or less we had to add an extra layer, an extra click, which is not needed for the protocol, but only to make it not too easy, because then users would log in without actually realizing they logged in. This is kind of the irony. If you make something super easy to use, then it becomes insecure, because people will use the fact that it's so easy to use to log you in without you knowing. It's the same thing as the button feature on the UB token. If you want to read more about it, there is actually a paper from 9 years ago describing this scheme. It's a very neat scheme, or you can ask any of our PhD students to demonstrate it to you. They're forced to use it. Well, the whole of KU Leuven is forced to use it. Is then everything solved? No. Of course, phishing, the problem is that we've been looking at authenticating Alice, but what about authenticating Bob? And more or less, all these protocols, they're more phishing resistant. You don't send the password, but if somebody really sits in the middle between Alice and Bob, and they convince you to run the protocol, more or less, this person in the middle can do a live phishing attack. And today, you can use an LLM to produce the code for you to do this. So we're going to see this more and more. So it doesn't stop you really from sitting in the middle and doing the whole protocol. If you lose your device, okay, this is really a problem. There's also local authentication. I will discuss that right away. There is sharing your device, which people do. So there is biometry to solve that. And there is interrupting the process after authentication. And then there is mafia fraud, so I'll show you some other problems. So I guess phishing, already discussed. The problem is there you authenticate to the wrong party, or you give your password, or you run the interactive protocol with the wrong party. So in the end, you have to trust the user, and it's just very hard for the user to do this. There also have been user studies with experts, and even experts can't tell sometimes whether something is a phishing request or a real request. So how should normal users be able to do this? Also, a mistake is sometimes made is mutual authentication between Alice and Bob is not the same as Alice authenticating to Bob and Bob to Alice. The two have to be connected in one session. It's slightly different. So devices are great, but if you lose your device, you have a problem. Okay. So first, you can't log in anymore, and second, then everything boils down to your extra password or PIN, which you have to have anyway. And if that is then predictable or put on a post-it, or somebody took a camera picture of you, and cameras are getting smaller and smaller, it's becoming, you still have a problem, of course. So you authenticate to the device, but even that can be vulnerable to shoulder surfing or to placing of cameras and so on. It's also interesting that you have to connect these two phases. This is a very nice example. So this was an academic talk, an attack on the 5,000 pages of EMV specs. So EMV specs is 5,000 pages. It's very complex. Maybe it's now 6,000 even. And so here is the attack. So more or less, EMV is designed for the whole world. So it's a credit card standard. But some countries, like the US, they don't like PIN verification. So especially in the first years, they wanted to have chip and sign. And even today, if you shop in certain shops in the US, they make you sign on kind of an LCD screen, as you know, as 20 years ago. So they, in the US, some banks believe that a PIN is only for debit, and a PIN should never be used for credit. And this is a religious belief. You can't argue about this. Okay, so in fact, EMV is a very complex standard because also Europay does things one way or did things one way, MasterCard does things another way, Visa another way. And so it also adopts a whole range of measures. And so one is the card holder verification method. How will you verify that somebody is the owner of the card? That can be a PIN code, that can be biometry, or that can be a signature on paper or on a screen. Okay, and so the Cambridge team, of which unfortunately Ross Emerson passed away last year. They had a fantastic attack. So more or less what happens is, as a user, you enter your card in the terminal, you enter your PIN, but there is no online connection, right? EMV was designed to be offline. At that time, in the early 90s, going on of the whole world online to issuer was unthinkable, okay? So the PIN was sent to the card, and the card would actually answer with yes or no, PIN is correct or not, to approve a transaction. And so what their idea was, you put a person in between the card and the terminal, so a device. And so the user enters, so you actually have a stolen card here where you don't know the PIN of, okay? So you enter a random PIN, 0000 on the terminal, okay? And then this device intercepts the PIN and says to the card, we're doing chip and sign. We don't check PINs today. And then you send an annotated command, which is the PIN was correct. You don't need the secret key of the card for this. So you just send a message, the PIN was correct, and the terminal believes that the card has checked the PIN, and the PIN believes that the merchant will have checked the signature. Voila. And so this is described in their paper. And so the problem is that the card verification method should have been mapped together with the transaction details, but it was actually an oversight in the EMV specs. And so 5 years later, David Nakash and his friends actually were given a chip card that was 10% thicker than a normal chip card. And when they X-rayed it, there was a second chip glued on top of the first chip, exactly implementing this attack. I think it's very funny to see that, you know, you publish something and then most banks say, very interesting, but nobody will ever do this. And then 5 years later, this was actually found in the field. I think that's an interesting lesson. And I think it's getting worse. So for example, beginning of this year, we published an attack on Google Fast Pair, which is a way of pairing your phone with your headset. So if you buy a new headset, if you switch it on, your phone will pair automatically. You don't have to enter PIN codes anymore or whatever, don't like first activate and search or whatever. It's like Fast Pair is really fast. So we found out that if people haven't paired their device and they sit on the train, you can actually pair it with your Raspberry Pi. And then you can send very loud noises in their ears, or you can listen to what they're saying, or in some cases you can even track them everywhere afterwards. Okay? And so we reported this to Google in September 2025, and they fixed it almost the day before the deadline, beginning of January, so they made another fix at midnight. And we said we were not going to release our tools because we believe it's really unethical and it can be abused. Within a week, there were like 17 apps implementing our attack. Okay, that's the reality today. So this took 5 years. Today, it's just people use LLMs and you describe a paper and they use the paper, give it to an LLM and gives them an attack with the app and everything ready. That's where we are today. Interesting times. Okay, biometry. It used to be something exotic, you know, like 25 years ago it was expensive. Today we all, or many of us use it for their phone, fingerprint or face recognition. Typically at the border setting, you claim an identity. Is this Alice? But there's also there a check of watch lists. Okay, so there is this list of 100,000, probably now more people who are not allowed to fly anymore in the US. And probably also in Europe there is those people. So this is a different check than is this person or is this person on the list? Right? Coming with a fake identity. And a similar system you have in the Middle East where there's countries with foreign employees. They can only stay for X years. And so they actually them in a database. And if they come back based on biometrics, they're identified or rejected. There is many modalities. So we see more and more face and finger. And that are the winners. Of course, you see also this Altman has iris scanning. This is the globe with this Persona company. Irises are much more random. But of course, again, if you have a high resolution picture, then you can actually reconstruct an iris and you can put it on a lens. You may also have seen in Germany that the Minister of Interior was called von der Leyen. Rings a bell. She was pushing identity cards with fingerprints. And she had a very nice press photo where she stood like this. And so hackers took the photo, zoomed in on her fingerprint, and then made a fake finger with her fingerprint on. This is the problem of biometrics. It's not really a secret. It's unique in the best case, but it's not a secret. So I guess in the long future, we'll have DNA. And people will, everywhere you show up, they just got a piece of your hair, and then they put it in a machine, and then they decide who you are, right? I don't know. I will not go to the steps, but you have always a registration phase and then a verification phase, and all of these can be attacked, obviously. So there is this false, you have a threshold, and below this threshold you reject, above you accept, and you have false accept. This means you accept intruders, and if you put your threshold higher, then this will go down, and then you have false positive or false accept. If you put your threshold lower, in fact, that will go up. So there is kind of always a trade-off between false accept and false reject. The interesting thing is for a fingerprint, this is at 1 or 2%. And something also most people don't know, you can produce universal fingerprints that succeed for about 25% of the fingers. So this is also the reason why after 9/11 in the US, they took your 2 fingerprints, but there was no quality check on the fingerprint, and it was only 2 fingers. So after like 6 or 8 years, they ripped out the whole system because the data was useless. They spent millions for nothing, and then they put the 5 fingerprint readers because the 2 fingerprints is just completely useless to identify things because false positive rates are way too high. But it's easy and cheap, and it's kind of easy to use, so it uses the patterns in fingerprints. So there is many readers, there is small templates, it's widely available. It is a problem if you're, say, a wood chopper or so, or you work a lot with your hands, your fingerprints may phase out. Also, some Asian women don't have fingerprints, so it's actually discriminatory to require fingerprints, so there may be failure to enroll. I think it's now disappearing, but I know when I moved to the US for my driver's license, I had to get my fingerprint taken in '93, and I was shocked. I thought that I didn't do anything wrong. Why should they have my fingerprints? Right? We now got used to this, but at least 30 years ago, I was shocked. And so, as I said, there is these universal fingerprints that work with 25% for every finger. And then people in biometrics, they don't do security testing. So then cryptographers do it for them. So a Japanese professor, Tsutomu Matsumoto, in 2001, actually, in the kitchen, he actually used the material for gummy bears to make a gummy finger. And this is his recipe is published online. So more or less, you can pick up a fingerprint from a table or a glass, or even from a picture in high resolution, and then you can make a gummy print. At that time, in 2001, you could fool something like 80% of all fingerprint readers with this. But people in biometry, they're not interested in security, they're just interested in selling you solutions. They don't test or crack stuff. I guess we now move to face. It didn't work. It was very difficult to do 15 years ago, but then they finally made it work with new techniques. Of course, it gives rise to mass surveillance. There is now Clearview that has illegally scanned billions and billions of photos on social media, and it claims now to be able to identify anybody in the public. If you walk around in London, like in Soho, you will see police vans that say we have actually facial recognition. In Europe, recognizing faces in real time is forbidden unless you're in a dangerous situation, like the Olympics, or a football championship, or a football game, or the Champions League final, or whatever. So there is now many exceptions when you can do it anyway. And I said real time, right? So offline, you can do it anyway all the time. So police can perfectly record everybody all the time, and if they a day later do the recognition, that's fine. So more or less, we'll end up, as Alessandra Christie wrote in a paper I think like 20 years ago, that in the future, we'll go back to primitive societies where the more important you were, the more parts of your face you could cover. That's the only way to get privacy will be to actually cover your face. I forgot to include a picture, but there is also something very cool called morphing. So you take two pictures, and then you make from this a third picture. And to humans, it looked like person one, and to the computer, it looks like person two. It's a very cool attack technique. And for this reason, you can no longer bring your passport photo yourself. So you actually have to go to the city hall and have your photo taken to actually preclude a morphing attack. And so in Belgium, the photographers were very upset about this because they made a lot of money charging €15 for a passport-compatible photo, and now it's included in the price in the city. The city actually now has its own camera. And so the photographers thought this was to undermine their business, but in fact, it's a security reason. Because it's not secure if you can deliver your own photo. Okay, so it's not so fun. The good thing is you identify the real person, so you can't pass this on. It's more or less user-friendly. It doesn't require less much effort. Who uses biometrics here to access their phone? There is, of course, a disadvantage if you cross the border. You can, in some countries, refuse to give your password and then you send back. But in many countries, it's legal to put your face in front of the phone or to press your finger on the sensor. So just you know. Okay, so that's a disadvantage as well, that you can, in Belgium, you cannot be forced to give your password, but you can put in jail for a few years if you don't want to give your password. And Belgian jail is not recommended. I don't know from experience, but what I see on TV, it doesn't look good. There is privacy risks, of course. Some people think it's intrusive, that people look in your eyes. There is a liveliness problem. Think of the gummy fingers. Think of people with big knives cutting off fingers. So my advice is, I should ask how many people of you use a fingerprint to authenticate and have financial applications on their phone? Are you not worried of people with big knives? Because they just steal your phone and then they hack your finger off and... Well, maybe it doesn't work, although putting a 9-volt battery over your finger with a small oscillator will actually make it look like it has a pulse. This has all been tried. So I would not combine these things. I mean, I don't give advice in general, but financial applications and your fingerprint on the same device, I would say think about it and then tomorrow decide whether this is a good idea or not. There is hygienic issues, there is discrimination issues. What you can do is derive a key from biometrics. If you do it securely, it's not as secure as people claim, but at least there is ways to make this more privacy friendly. The other problem, still talking about authentication, is you can have a whatever protocol. If it's remote authentication, the adversary can just cut the connection and take over the line. Right? This was done initially in mobile phones because mobile phone calls were very expensive. So people authenticated first, and then you just jammed their phone and you took over, and now you could place a call at their expense. Right? I can also tell you in the break how we did it in computer science. Our professors logged in and we unplugged that cable and plugged in our cable. I never did this, but some of my colleagues did this. And so how you could bypass authentication like this. So this is a problem that the communication is decoupled from the authentication. So, and the solution is authenticated key agreement. This is why you always have to authenticate the user and establish a key to then apply authenticated encryption to all connections. Right? So you have to link those two steps to avoid connections being taken over. And then there is this impersonation problem. I mean, I already gave you a preview with the attack on the credit card, the wedge attack. So this is an attack which was demonstrated live in the war between South Africa and Namibia. So South Africa had this identification friend or foe systems. And so if you give a right answer, you don't get shot at. If you give the wrong answer, you get a rocket shot at you. That's not so healthy. And so the Namibians had their own defenses, a bit more crappy. They had their very crappy planes. So if they would fly to South Africa, they were clearly more vulnerable. They would get this challenge and they didn't know the response. So what they do is they found a nearby ground station of Namibia who found a nearby South African plane and asked the question. And the plane didn't want to get shot at, so it gave the answer. And then they said, thank you. And so it actually had the answer. So this is, in fact, known as the mafia fraud. You can also look at Wikipedia on the grandmaster chess problem, how you can teach a 6-year-old to play two grandmasters in two different rooms and to either win from one of them or to draw against both. Okay, and it's actually also a very big problem in payments. So you can go to a shop and you think you pay for a newspaper or cigarettes or sweets, and they use your authentication to actually buy diamonds in Antwerp. And it's the same attack, right? Of course, the shop has to be in it, but you know, it's cheap to make a pop-up shop that sells stuff. And then with this, you can actually buy diamonds. And of course, diamonds, you can put in a pocket and go across the border so you can export high value. So this is a real problem as well. And so the only solution is not more cryptography. The only solution is to prove that you are nearby. And this is very hard because you now need physics. So we call this distance bounding. So you try to prove you're nearby. I know that some credit cards have this as optional. So also these cards, the Marfair Plus cards, have this protocol in there if you want to activate it. But it's not very secure. It only works if the intermediate device is a smartphone. It doesn't work if I put hardware in there, then they can't detect it. But this is a real problem also for car keys, by the way. This is also how you steal cars. You go to a front door, you hold antenna to the front door where somebody has their keys in their pockets, and then the second antenna to the car, and this is how you actually can open and start the car. There is nice videos of this on the internet. So again, you have to prove that you're nearby to stop this attack. There is no cryptography that can do this. Let's move on to key establishment for the last half hour. So I guess I motivated the problem. So how to do this? Using public keys, secret keys and public keys. And then how to start public keys, that we'll discuss tomorrow morning. That motivates in the talk of tomorrow morning. So symmetric keys don't scale. That's what you read in every textbook. Of course, if you have, in this case, my simple example, you have 4 nodes and you want to have each of them share a key, then you need already 6 keys. But if you would have 100 nodes, the formula is n times n minus 1, the number of pairs over 2. So you have actually already 4,950 keys. So this is what people say, you can't use symmetric key in any real system because we have too many systems. It's of course wrong Because what you do in symmetric key is you have a key distribution center, a central party, like what we have in GSM, the authentication center that shares a key with every user. And if two users need a key, they can actually request one. Well, GSM doesn't provide this service, but in theory, it could provide this service. It could give you a key to encrypt your call end-to-end. It actually doesn't, but there would be no technical reason why it should not be done. It's more a law enforcement reason. Law enforcement doesn't want you to have encrypted calls using symmetric key. But so it actually does scale. The only problem is you have this central party that has all the keys. And of course, if you think of Snowden and the NSA, then everybody will go after this thing. So people have now been thinking maybe you should have like 5 key distribution centers and use multi-party computation or so to compute stuff so that you have to compromise all of them. So it could be possible if we don't find any good post-quantum schemes, then we can still move to such a world. But so symmetric key does scale, but it's a very different architecture. So, but in cryptography, we move problems to keys. So the real problem is how to manage those keys. It's really a difficulty because this interacts with the applications. And so hopefully users don't see it too much, right? If you have to explain to a user that they have some problem with a key, it's not your best day. It's just, so ideally it should all be transparent. So I like the GSM system because, in fact, it was way ahead of its time. It was the first large-scale system. It now has billions of users. Of course, they're not in one system. It's all per operator, okay? And so, more or less what you have is in GSM, you get a random number and you send the MAC back, so as we've seen before. So this is how users are authenticated, because this was important. Because, again, for the young generation, phone calls were expensive. I mean, it was not unusual in the late 90s. I have a 250 or 300 euro phone bill. If you were traveling a lot, making calls abroad was very, very expensive. So they wanted to be really sure that you were the owner of this phone, so they wanted to authenticate you. And this key actually sits in your SIM card because the operator doesn't trust the mobile phone manufacturer. So what actually happens is in the SIM card, you have the random number is being put in a different function. So this MAC function is called A3, and this is A8. What you do with this is you derive a session key, and this key goes to the phone, and this is to encrypt the calls. So, and the encryption in the phone happens in hardware, but the important secret, the KI, the user key, this actually sits in the SIM card. And so even if you hack the phone, you will find the session key, but you will not find the long-term key. That's more or less how GSM worked. So of course, it means that I put here the base station, but of course the real key database doesn't sit in the base station because it's like on top of a church tower. It actually sits in the operation center of the operator, right? There is an authentication center there where you go. Yes? Is that the reason that the SIM card has a different key compared to the phone itself? Yes, it's the same question my 89-year-old mother asked me when her phone got blocked. So the SIM card is a separate security system, right? So it activates your subscription and it's controlled by KI. There is a PIN for it. And if you enter 3 times the wrong PIN, you have a PUC. But that's more or less the operator. If you then lose your PUC, you have to contact your operator. I mean, Apple will not know anything about this, or Samsung, or whoever your phone producer will know nothing about this. It's a security system of your subscription, right? Then on your phone, ideally you have a second system for logging in where you have a PIN code, but that's locally to your phone. And that's, if you had a problem there, you could reset your phone, or in theory, go to Samsung and say, I have a problem with my phone, right? But they're completely different.
So the key for the SIM card is part of the encryption as well, because if I understand this model well.
No, the PIN is independent. You can set it and change it. In most operators allow you to change it, but it's completely independent because the PIN just means that the computation will be done. So it's kind of so there is a PIN. Typically what is done is, I would say if it's an old card, it will be encrypted with triple des or so. And then the encrypted value is in the card. And so your PIN is taken, encrypted, and compared to the encrypted value that's stored. And then the PIN is correct. And now after 3 times incorrect entry, the PIN is blocked, and then you have to enter the PUC. But it's completely independent from your biometrics or your password or whatever you use for your phone. So, of course, these keys, they don't sit in the base station, as I said, they sit in the central place. And then there is also a very nifty system. If you roam, then actually they will never give you a long-term key to, say, Italy or Turkey or wherever you go. They will only give the challenge, the response, and the session key. That's called the triplet that will be sent to the mobile operator. They get a few of those. And for 3G, it's a quintuplet, because there is also an encryption key, an integrity key. So it's a bit more complex, but more or less the principle is very simple. But it actually scales. The only problem is we still haven't seen an operator that lost all its keys, because then everybody has to come and get a new SIM card. What we have seen is that, okay, I'll have to be careful because this is recorded. Let's say a random country in Europe, not so far from here, every Friday evening, the government knocked on the door, give us all the keys that you produced for the SIM cards this week. And I told this to some people who had access to the Snowden documents. And they looked for this particular company. And they found out that this was, the story I tell is from the 90s, that later on this interface was automated. So the government could call an API to get those keys of the week. And guess what? GCHQ found the interface too. And they also got the keys. And that's in the Snowden documents. Okay? And there was also an employee working for a secret service from Europe, fired after he was caught in Singapore with a CD with all the keys of another country. So these secret keys are not so secret. There is also one operator who gave the same key to every user, which is a lot more convenient, and you don't have to do key management. Okay, so much about GSM. Yes?
Like, for example, like, first, like, is the same key is being used for, like, all sessions, like, one session key is being stored, like, on whatever device or the system, like, is the exactly same key that is being used again and again?
Well, if you have a call, every time a new key is being generated, okay? So if you, from 3G on, there is an encryption key and a MAC key, okay? So there's two keys, and every call is a new one. But if you send data, there is a notion of, like, how many bits have been sent, and then you do a new key. So the idea of a session key, we'll discuss this later as well, is that you want to reduce the time you use a key. So if it's compromised, the impact is limited. Okay, and so in general, the operators believe that sending such a session key to a phone is very insecure because they don't trust the phone. So they would never send KI into a phone or to abroad to another operator. They would never do that. So assume you have a long-term key. You still want to, between Alice and Bob, you want to establish a session key. And why? So people like myself and Tim, we like to break stuff. Okay, but if you keep changing your key, you make our job harder. And if somehow a key leaks, well, then we find, maybe we can find it, but then we don't find the next key. So you want to make as many keys as possible. And this is, the financial sector takes this to the limit. In the banking world, at least in Europe, every transaction has its own key, right? And so this is quite messy. In the US, what they do is they XOR counters into keys, which is much less secure to get different keys. That's not something recommended. But so you want to change keys all the time to limit the impact and to make cryptanalysis harder. So imagine you have long-term key, then you will make a temporary key for this session, whatever a session is, a browsing session or a call, together with a timestamp and say this is for Bob, and Bob will decrypt this, get the session key, check the time to make sure it's not an old message, check it's intended for him, and then answer and say, here is my timestamp, hi Alice, nice to meet you, and hello message, so to confirm that the key has been approved. This is called an example of such a message. I think we now know more or less how to design these things, but it was very difficult in the 80s because sending a bit was expensive. Okay, modems were like 1200 bits per second, or by the end of the 80s, 13,000 bits per second. Bits per second, yes, not kilobits per second or not bytes per second. So 13 kilobits per second, so 2 kilobytes per second. And so people were saving and sending as little information as possible, and that gave rise to many attacks on these protocols. Okay, so, but before you have a long-term key, and after this interaction, you now have a short-term key, which you can use for a while and then throw away. And this is the principle which you find everywhere. in all network protocols. So this is in Wi-Fi, in Bluetooth, in banking protocols, in IPsec, in SSH, in TLS. We call this session keys. Also, a very important system is Kerberos. Kerberos was designed by MIT for one of the first distributed systems in Project Athena. And so there the idea is you have a user that shares a key with a sender. In fact, a user shared a password, and this password is then hashed to make hopefully sufficiently random key. And the server has a key. And so if a user wants to talk to a server, she says, "Hi, I'm Alice. I want to talk to Bob." And here is a nonce, which is a value that should not repeat. And what it gets back, so the server makes a session key, and it will encrypt the session key with the key shared with Alice. We'll add the nonce. We'll say this key is valid for, say, 1 day, and this is the key for Bob. We'll also produce a ticket. A ticket is something similar. It's encrypted with Bob's key. It's the key. So it's a key you share with Alice, and it's valid for 1 day. And so those two things are sent to Alice. Alice will decrypt this. She gets the key. She checks the nonce. She checks it's for Bob, and she checks it's valid, and she will store this. And then she will forward this ticket to Bob because she can't decrypt this. She doesn't know the key. And she will encrypt her name and a timestamp with the session key. And then afterwards, Bob will, of course, from the ticket, he will get the K, check indeed it's for Alice, check it's still valid. And then he will then take this message with the key, can decrypt it, check indeed comes from Alice, it's still valid, and then send an answer. I go a bit fast, but you can look at it later and see it makes sense. It's a widely used protocol, as you will see. So before Alice has a password, and then which she has to enter, and then afterwards she gets a ticket. With the ticket she can authenticate to Bob and have a secure communication. And if she wants to, later in the day, she wants to talk to Bob again, she doesn't have to enter a password again, she can just take her ticket which she kept and she can set up a new session. It's what we call single sign-on. Very fancy, but that's just what it is. You log in once to get a ticket, and then this ticket can be used all day. It's very user-friendly, but of course, if your system is hacked, then the ticket is there and somebody can use the server Bob the whole day. There's always a trade-off of single sign-on, that you trade convenience for security. But nobody wants to enter their password the whole time, right? That's the idea. So this is what Kerberos achieves. So it's a single sign-on system, but then you can say, well, what if there is multiple servers? Then I have to still enter my password for every server. Then the answer is there is no problem in computer science that cannot be solved by adding a level of indirection, except too many levels of indirection. Okay? So you have a level of indirection, which is that you, instead of getting a ticket for an application, you get a ticket for a ticket granting server. And with that ticket, you can get new tickets for any application. So you only have to enter your password once when you have to get the ticket for the ticket granting server. So in the morning, you log in, you get a ticket for the granting server. You store this, you cache this on your disk. It's not very secure, but that's what you do because it's convenient. And then the whole day you can, if you need a new service, you go to the TGS and then you can run the protocol. That's more or less how it is. You think like, is anybody using this? Well, it is because it actually became an RFC. And then Microsoft stopped their long-term effort in the 90s to boycott this. And they put it into Windows 2000, and they called it Active Directory. Ever heard of this? Okay, that's actually using Kerberos. Of course, they made sure that what they implemented was not compatible with any previous implementations of Kerberos. And then a bit later, macOS added this, and there have been several attempts to actually make public key versions of Kerberos, but so far they've been failed miserably. With one of my students, we broke one of the versions, but it still seems like, very late 80s, early 90s stuff, but it's still running. Everybody's still using it because, of course, it's very efficient. So, of course, if you use passwords, it's vulnerable to password attacks. It doesn't do authorization. And in the old versions, it didn't have authenticated encryption. It just had encryption, so it was old crypto. But I guess these things have hopefully been solved in most deployments. But I wanted to show it to you because most people actually don't understand the cryptography behind Active Directory and don't know it's actually a very old open source project. Although open source, again, for the young generation, in the early 90s, you could not export Kerberos code from the US. Even with the encryption code removed, it was seen as ammunitions. And you could, until 1999, you could not export Kerberos code. So in Europe, you had to re-implement it ourselves. You heard of Diffie-Hellman? Fantastic protocol. So Crane explained it to you, so I don't have to explain it again. So it's really amazing. And you may know that there is 4 Turing Awards for cryptography. The Turing Award, like the Nobel Prize for computer science. So the first one was given to Vivesh Chandra Edelman for the RSA algorithm. And then the next one was given to Mikhaili and a few other people, I think, for general knowledge. And only then Diffie and Hellman got their Turing Award for Diffie-Hellman. Very interesting because they invented public key, but they only got a Turing Award many years later. And then this year the award went to Brassard and Bennett for the QKD protocol. But so it's a fantastic protocol. So you have an open channel, you have a chat, and suddenly you share a secret key. But then the interesting question is, how does Alice know that she shares this key with Bob? And the answer is she doesn't. So people realized when they could implement Diffie-Hellman, this was kind of the first implementations were late 80s, that we actually have a problem. And so the way, for example, Swift solved it is they computed the hash of the values, and then they picked up the phone and they knew the people at the other side, and then they read the hash values over the phone to make sure that they were talking to the right person. Okay, so this is, of course, so the attack is the following, right? The NSA sits in the middle, or your favorite attacker, and runs Diffie-Hellman with you and with the other side, and so there is a key between Alice and the attacker and between the attacker and Bob, and so you wouldn't notice this. I guess you're all familiar with this if you use SSH. Every time the server key changes SSH, you get a warning saying, hey, my key has changed, do you want to check? And what do we all do? No, it's fine. I'm not going to go down to the sysadmin or go up to the stairs and talk to this guy. He will shout at me and whatever. So, or she will shout at me. I'm just going to leave it and it's okay, right? We're optimistic, called optimistic security. But so more or less, that's called trust on first use. So you hope that the NSA is not there now. You're an optimistic kind of people. But what you really should do is go to the sysadmin and check that this value is correct. Okay, so in the early 90s, even before Diffie-Hellman was widely deployed, Belovin and Merritt actually made a very nice extension that's not widely known, although now there is lots of research on this, very little deployment. The idea is that if you encrypt now Diffie-Hellman with your password, you can also authenticate. And if you do it in a clever way, and this is, I don't have time to explain you the details, but if you do it in a clever way, you can actually not guess passwords from the transcript. So imagine that you have intercepted this, you can guess a password, but if you take the password and you decrypt this, you get a random value, so you don't know whether you have the correct password. So you cannot do an offline attack against this. This is very cool. Of course, you can always do an active attack, so you can claim to be Alice, guess the password, and then, of course, see whether it works, right? That you cannot stop, but then you can say, after X attempts, we will block this. So, but passive attacks are blocked by this. It's actually perfect for the internet because the servers all have authentication, but the users have passwords. They don't have passkeys or tokens or public keys or certificates, so we don't have any of this stuff. But somehow it never got used. I think part of it was patents. There was a whole variance of schemes with patents on it. And then in the end, by the time that it was clear we can do it without a patent and we have a nice solution, then like everybody had been rolling out all the other stuff and nobody bothered anymore. So it's a kind of an example of nice technology that never made it. Today, people write papers about it called PAKE, Password Authenticated Key Establishment. And there is hundreds of papers of all the variants, but so beware, it may be a patent minefield. I don't know how the situation now is, whether the researchers now still take patents, but that's the reason why it actually failed in the 90s, because there were too many patents and people said, the IETF said, we're not going to touch it. Okay, what did the IETF do instead? A nice protocol designed by Diffie, Wiener, and Van Oorschot called station-to-station protocol. You do Diffie-Hellman, and then you sign the Diffie-Hellman. So Alice, Bob signs with his private key, Alice with her private key. And then since you have a secret key anyway at this stage, why not encrypt everything right away? And this is authenticated encryption. So this is very nice because if you look at the transcript, you see 2 random values and then you see ciphertext. So you don't see what's happening. So this is more or less kind of how you should use Diffie-Hellman. You should sign the values to authenticate. And then as soon as you have the keys, you should encrypt. It's really the Rolls Royce of protocols. It has all the properties you want. And it has a fantastic feature, which is that, I forgot to include it on the slide, but what people used before was your browser made a session key, took the public key of the web server and encrypted it with that key and sent it over. That's how you used to establish a session key with a browser until 2013. And what we discovered from the Snowden documents is then that the NSA knocked at the door of Google and said, you have this nice key with which you can decrypt all session keys. Can we have a copy of that, please? And if you don't give it to us, we'll actually put your CEO in jail. If you talk about this, your CEO also goes in jail. So you can see that Google gave this key very quickly, and everybody else did. So this is a problem. And so this protocol solved this, because if here the NSA knocks on the door, what they can ask for is, in this case, if this is Google, they can ask for the private signing key of Google. And if they ask for it, then Google has to give it. But every time the NSA uses it, Google will know, because the NSA has signed something that Google hasn't signed. But in fact, the NSA cannot read past communications. In the previous case, once you got the Google key, you could go to everything stored in Utah, which you couldn't decrypt before. You could take the encrypted session key and decrypt it again. While here, if Google is smart enough and you're smart enough to throw away X and Y after the protocol, there is no trace left. And if you come 1 second later, there's nothing you can actually use from after the X and after the Y. Even the NSA cannot compute alpha to the XY. And so they actually can't do anything with their key. They can only affect the future. We call this forward secrecy. And this concept was invented by Diffie, Wiener, and Van Oorschot in 1992. And people said, cool, but we're not going to do this because the previous protocol I showed you is one RSA encryption, one decryption. And here you have 1 exponentiation, 2 exponentiations, 3 exponentiations, a signature, signature verification, signature, signature verification. So this protocol is 4 times more expensive for both sides. So Google said, very nice, we're not going to do this. Because I know, because one of my students, Emilia, who's now senior director in Google of Director, heading the cryptographic developments, she went for the summer to Google and she implemented this kind of protocol and she made it like almost faster than RSA, not faster, only 20% slower. And we said, fantastic job, Emilia, but you really think we're going to put in 20% more servers? 20% more, you know what that costs, Emilia? And she said, no, well, it costs too much, we're not going to do it. Then a bit later, Snowden happened in June 2013, and by November, Google and Microsoft announced that they would switch to Diffie-Hellman. And this is why Diffie and Hellman only got their Turing Award after 2013, because nobody bothered to implement it because it was too expensive. Okay, it's a very nice story. Of course, on the internet, nobody ascribed it to Diffie, Wiener, and Van Oorschot, so people called something Ike and TLS, and they kind of borrowed the ideas, made a few changes. So you add a PRF to the random function, you hash the master key, but more or less it's the same thing. In the end, if you look at the high level, you sign Diffie-Hellman exponentials with some extra stuff, and this is how both IPsec and TLS work today. Well, with the difference that, of course, the client doesn't sign, because you don't have a certificate and you don't have a signing key. But more or less, if you understand this, then you understand Ike v2 and the TLS protocols. So it's fantastic. Can we do better? Yes, there is a Signal protocol, but I'm running out of time for this. But Signal actually is the protocol designed by Moxie Marlinspike and Trevor Perrin. They got an award for this, the Left Chain Award, because it's also the protocol that's used by WhatsApp and all the other messaging services. And so more or less, they added one other thing. So they added also post-compromise security. So this means if your phone gets confiscated at the border and the border agent takes a complete dump of your memory, then you can actually, well, that's tough. You better had deleted your old messages before you cross the border. That was your problem, but you're supposed to do that. But even if they have the full state of your device now, once you leave the border and you use Signal again, after a while, they will lose track of what's happening. And it's called post-compromise security. Of course, if they put malware on there and they can see every messaging clear, then this doesn't help. But if it's a one-moment compromise, then in fact, you kind of recover. Okay? I don't have much time to explain it to you, but it's very complex. You have long-term secrets, mid-term secrets, and short-term secrets. And more or less, you make a whole package of this, and you send those to the server. And so if Alice wants to talk to Bob, she says, give me the package of Bob. So this can be done asynchronously, so you need a server for this. And then, so you get the package of Bob, and then you make another ephemeral key, and then you make a key by combining in several ways short-term and long-term keys, and medium-term keys, and short-term keys, and whatever. You make a lot of combinations. This is not random. People thought about this very carefully. But by doing this, you can actually get post-compromise security. I don't want to show this to confuse you, but just to show you that even getting this one property, you need to make it a lot more complex. But then again, your phone does it, right? It's being done, and it doesn't cost that much. Of course, then how you authenticate the long-term secrets with the QR code, you're supposed to do this. Otherwise, again, you have the same problem. There is also lots of tricks when you keep applying one-way functions to key material. There is also sending and receiving keys, but so more or less if you compromise this key, you can't go back and find that key or that key. So all the time you keep like applying one-way functions to your keys. And this is why it's called double ratchet. This is the first ratchet, or this is a ratchet. If you don't know what a ratchet is, it's like something to move something up, a krik in Dutch. So this is, you keep applying one-way functions to your key so that if one get compromised, you can't go back. And the same thing you do with Diffie-Hellman, so you keep sending new values and upgrading your keys with Diffie-Hellman. This is more complex, so it happens less frequently. This happens for every message. But it's all very tricky because messaging is asynchronous. So it means that if you hashed your key before you got the message, of course, then you can't go back. So you have to make sure that you don't hash too far. So there is a lot of clever engineering in there, but more or less, this is how it works. So just to get post-compromise security, you have to add a lot, and to make it asynchronous, you have to add a lot to station. It's not just one thing, and people had to work very hard on it to make it work. And one of the problems is that, so Signal and WhatsApp are already post-quantum, but in fact, we still don't have a post-quantum Diffie-Hellman. So we can encrypt the keys in addition with ML-Chem, right? So that you have to also break a lattice scheme. But imagine that somebody has a real-time quantum computer analysis, so Diffie-Hellman no longer works, and then in fact we don't get this forward secrecy and post-compromise security properties. So this is still actually a very good research problem to work on, but it's probably a hard problem because we've been now working for close to 30 years on post-quantum systems, and nobody has been able to build a new Diffie-Hellman scheme. So it's probably harder than making a chem or a signature. Okay, so time to wrap up. So how do you analyze protocols? Well, you can, of course, you have to first find out what the specs are. What are the messages, what are the actions, what are the goals, and what are the assumptions? So this is very often a problem. We also see often problems that people take a protocol and then they put it in a new context, or the assumptions change, and then the analysis no longer holds. So you can stare at the protocol and find mistakes, but that's not really acceptable today anymore. A few protocols you can use information theory, but this is very rare. So mostly we boil down to what's called cryptographic proofs. So where you make complex games, and these proofs are very long and complex, and it's easy to make mistakes. But you can do very cool stuff. But if you go to a cryptographic conference today, you will find papers with pages and pages of proofs where they try to prove that the protocol has certain properties. And the definitions can take already 5 pages, and then the proofs take pages and pages to show that, of course, you never prove absolute security. You prove that if you can break this protocol, you can violate a mathematical assumption. But there is also tools for formal methods, and 20 years ago, they were unusable, but today there is 2 very nice tools. There is like the lightweight tool called ProVerif, and if you want to find out more, Giorgio, one of my students, is an expert in this, can explain to you about this. So it's easy to learn. It may produce false attacks. So if it says, I broke the protocol, you have to double check it yourself because it may not have. So it's a bit optimistic, but it's very fast. And then there is another thing, which is kind of the life work of Cas Kremers, a Dutch cryptographer who is now in Saarbrücken. So he made a very complex tool called Tamarin, which takes a very long time to learn. But actually can analyze very complex protocols. It still can't do everything. Using this used to be very hard. It turns out that today you can actually, with an LLM, use these things. Instead of taking a 6-month course, you can actually use an LLM and say, I want to prove this protocol with Tamarin. Please give me the input that I need to give, or what kind of definitions I need, and so on. It's still not going to be a piece of cake, but I would say in the past I would have told my students, don't, because you don't have an extra year for your PhD. But today, actually, for some protocols that you can't do with ProVerif, you could actually probably, in a reasonable time, make progress with Tamarin. Okay, so time to wrap up. So properties of protocols are subtle, and I didn't have too much time to explain this, but we didn't even go to definitions. But if you look at papers, for example, there is 7 definitions of freshness, what it means for a variable to be fresh. And like, you know, depending on what you expect and what you want, so it's not an easy area. There is many standardized protocols, but ISO standardized them at very high level, so they're not bit level compatible. IETF, at least, and Bluetooth and so on, and EMV, they specify everything up to bit level, so they really give you compatible implementations. And what is really difficult is to find out which properties you need. Or I have a protocol for application A, does it also work in application B? And I think these days are over, but in the 90s, when I was a young researcher, I got many emails from people who said, I made this new block cipher, Mr. Preneel, can you please look at this? I made this new stream cipher. I have a new cryptographic system. I have a new public key system, but I don't see this anymore. But I still find a lot of people who design new protocols. So this is why I introduced rule number 1 of protocol design, don't. Okay? If you want to design a protocol, you have to do a PhD. And after 3 or 4 years, you'll be able to design a protocol. But most people think, oh, they can do this. Well, the rule is don't. And even simplifying things in existing protocols can give rise to disaster. Okay, I think I'm going to stop here. Thank you very much for your attention. I wish you a smooth evening. I hope you find a cool place to relax. And we see you all back in this air-conditioned room tomorrow at 9 o'clock. We can still do questions, but people also can free to go if they feel to, because I run a bit over time. Yes? Okay. Yes. Yeah, the slides will be available. I mean, I made my slide this morning. They should be online already. If not, they will be soon. Also, my slides, I will mail them tonight, and they will be available online tomorrow. No worries. So have a good evening. Thank you.